I'm Bob Duhamel, and today I'm going to answer the question, does Ohm's law work with alternating current? Now this question comes up because I found a website called InterestingEngineering.com that blatantly says Ohm's law does not work with alternating current. Well, let's find out if it does. So let's make this circuit. There is an alternating current source. I will make that 10 volts, and we'll go through a resistance. Let's make that 10 ohms. And what do we mean when we say 10 volts alternating current? Well, in alternating current, we have current that's going back and forth and voltages that are changing. And typically we're talking about a sine wave. And when we talk about voltage without any qualifications, AC, we're talking about what's called RMS voltage. If I take this, that's going to be 0 volts there. And let's say it goes up to some voltage and down to some other voltage. If I take several voltages along this trace here, and I square those voltages and then take the mean, which is a type of average, so root, mean, square, so I take all the squares, I average those together as a mean, which simply means your typical average where I add all the numbers together and divide by the number of numbers, and then I take the square root. I'm going to get a number we call the RMS value, and in the case of 10 volts RMS, I am going to find that my peak voltage is 14.14 volts. So it peaks up at positive 14.14, and the negative side is going to be negative 14.14 volts. So peaks at 14.14 minus 14.14. If I take the voltages along that, take the square root of all those, average them, then square that, I'm going to get 10 volts. So 10 volts RMS is describing that wave. But in a nutshell, Ohm's law says if I divide my resistance into my voltage, I get a current. So I have alternating current. And if I divide 10 ohms into 10 volts RMS, I am going to get 1 amp RMS current. So just have to remember that our voltage is changing all the time, so our current is changing all the time, so that is also an RMS value. And also, if I freeze time, I find, let's say at the moment that this happens to be, there's our curve again, let's see, we're right at the peak at 14.14 volts. 14.14 volts, divide 10 into that, that's going to give me 1.414 amps. So my current is going to peak at 1.414 amps, but my RMS amperage is going to be 1 amp. So if we freeze time, an alternating current circuit looks just like a DC circuit. You can only tell an AC circuit from a DC circuit if you let time go by and see what happens as time goes by. So you can apply Ohm's law to an alternating current circuit. We do it all the time. Now, let's make this circuit a little different. Let's put out here a inductor. And let's make that inductor 100 millihenries. And now to do this calculation, I need a frequency, and I'm used to our American standard here, so I'm going to make that 60 hertz. Most of the world uses 50 hertz, but here we use 60. That's what I'm going to stick with. Now, how much opposition to current flow is that going to offer? Now we know that there's some resistance, but I'm not going to specify that. In fact, just to simplify things, let's say there's no resistance, because that really makes it complicated. I talk about that in a previous video titled Inductors in AC Circuits. But let's just assume there's no resistance just to simplify things. How much opposition to current flow is that offering? Well, we call that opposition to current flow inductive reactance. It's caused by the fact that when I try to send current into the inductor, that causes a magnetic field to build, which causes the magnetic field crossing all these turns of the inductor, creates a current which pushes the opposite direction. And that's constantly changing because the current in is constantly changing, the amount of voltage across the inductor is constantly changing. But we can calculate what it's going to be, and that's going to be, well, we represent our reactance by X. And I'm going to put a little subscript L there. X sub L equals what? 2 times pi times our frequency times our inductance. So X sub L equals 2 pi FL. So I can calculate my opposition to current flow with that fairly simple formula. So here we go, 6.28 times 60 times 0.1 equals, because 100 millihenries is 0.1, so 6.28 times 60 times 0.1 gave me 37.68 inductances. Well, that's ohms. We measure inductive reactance in ohms. Why? So we can use Ohm's law with AC circuits. So now we have 37.68 ohms of inductive reactance, and I can calculate the current now because I know we have 10 volts RMS. So here we go, 10 divided by 37.68 equals, and I got 265, let's draw our alternating current there, 265 milliamps RMS of current. So the current is constantly changing, our voltage is constantly changing, the voltage across here is constantly changing, the current and the voltage are not happening at the same time. So when the voltage is high, the current is low. When the current is high, the voltage is low. It's a big mess. Talk about that in the previous videos. But we do get a number which would be 265 milliamps RMS current. So the current's going to be higher than that and it's going to be lower, but the RMS average is going to be 265 milliamps. So we use Ohm's law in alternating current all the time. So saying that Ohm's law does not work with alternating current is just simply wrong. Go to look in any electronics textbook and you'll see plenty of Ohm's law in alternating current. If you found this video useful and informative, please give me a thumbs up down below. It really helps the channel. And subscribe, because that not only informs you when I put new videos up, but it really helps the channel also. And a big thank you to my patrons at Patreon. I could not make these videos without your support. If you want to help me put these videos online and keep real vocational education free at vocademy.net, you can go to patreon.com/join/vocademy and pledge your support. And again, a big thank you to my patrons who make this possible, and a big thank you to everyone for watching.